Hello, Chapter 5, Section 4, working on exponential functions and the derivatives of the exponential functions. So first thing we're going to do is let's talk about properties of the natural exponential function, and then let's go into what the derivatives may look like. If I took an equation y equals e to the x, I could do natural log of each side. And when I do that, the x could come down and the natural log of e goes to 1, and I'm left with this type of phrase, x equals the natural log of y. Now, solving exponential equations, solve to 3 decimal places. What we're going to want to do is take the natural log of each side. That's going to allow this x value, which is in the exponent position, to come down and get down to the normal level where we can work with it. So right now it'd be kind of difficult to guess what do I need to raise e to get 18. But with a little bit of algebra here, we can make the answer more apparent. So let's take the natural log of each side. The reason I chose natural log is, well, I can bring the x in front, and then I'm left with natural log of e equals natural log of 18. But the natural log of e would be simply 1, and I'm left with x then equals natural log of 18. And that is my answer. This would be some numeric value that we could calculate. Part B here. Before I take the natural log of each side, I think it would be extremely handy to get rid of that 5. So let's divide by 5, and that will allow us to get e to the x kind of isolated. Now, I want to get to this x, but I want to bring the x out of the exponent position. So let's take the natural log on both sides, and I'd have natural log of e to the x, natural log of 3. Once again, this turns out to be x because x comes out front and we get, or it becomes a multiplier, and I get x times natural log of e, but that is 1, and this will equal natural log of 3. Therefore, x is equal to natural log of 3. Plug it back in up on top and you'll see that that works. I might have missed one. Letter C there. Solve equations. Well, let's just kind of take the normal equation solving steps. What I'm trying to achieve is to get e to the x all by itself. So we subtracted 9. Next, let's divide by 4. And we're sitting with e to the x equals 4. Now, to actually find out x, let's introduce a natural log to both sides. And natural log of e will result of e raised to the x will be just x, and I'll get x is natural log of 4. Notice if I replace x here, I have 4 plus e, natural log of 4, and then this plus 9. This is multiplied, sorry, this is multiplied, then I get e natural log, which will bring out just the 4, and 4 times 4 is 16 plus 9, gives us the 25. More solving. Let's take and divide by 21, get e to the negative x by itself. That'll give me e to the negative x equals 2/3, because they're both divisible by 7. Let's introduce a natural log to each side to allow that x to come out of the exponent position. This will go to 1, and I'll end up with a negative x equals natural log of 2/3. But I want to know about x, not negative x, so multiply both sides by a negative. Now, if you want to get fancy, an alternate option would be, this would be one answer. This would be an okay answer. But perhaps I should deal with this negative. I could bring it back up as a power, couldn't I? And I could say that x is equal to the natural log of 2/3 to the negative 1 power. But that's equivalent to saying I've got the natural log. Negative 1 power to each of these will basically turn that fraction upside down. I could think if I have negative 2 to the first, 3 to the negative 1, and that sends the 3 to the top and the 2 to the bottom, and that's how I ended up with 3 halves. This could be quite possibly another alternate answer provided, you know, in a multiple choice type question. Letter E. I want to get that x, and you know, actually this is quite easy. This e and natural log will cancel each other out, and I'll just get 6. So if I looked at this, if x is 6, what is this equivalent to? Well, it's equivalent to 6. That cancels away. E to the 6th equals e to the 6th. That doesn't quite look right, does it? I kind of wanted to show you that. Well, I'll have to think on that. Letter F. Try to write it in exponential form and then solve for x. So another way to solve logarithmic equations, we have natural log with this base of e. Well, let's go e to the power will result in 4x. Our power is 2, right? So I'd have e to the second equals 4x. And then I would just need to divide by 4. And that would give us x is equal to e squared divided by 4. A numeric answer. Letter G. What would be easiest, perhaps, is to take this 2 and use that property rule and bring the 2 down in front. So we'd have 2 natural log of x minus 2 equals 12. Divide both sides by 2, and we'll have natural log x minus 2 equals 6. Now I can apply base of e to the 6th equals x minus 2. Add 2 to the other side, and I'm going to end up with x equals e to the 6th plus 2, a numeric answer. Okay, now for derivatives. The derivatives of natural log functions. Let u be some differentiable function of x, and we can talk about general case and a little bit more broader case. So what if I just had e to the x and I wanted to take the derivative of it? The derivative of e to the x is e to the x. It is just itself when you take the derivative of e to the x. Now what if I had e to the u? The derivative of that will be e to the u, so it is itself. It is itself. So here, it is itself, but then I've got this little chain rule going on, and I'll need to take the derivative of u as well. So e to the u times u prime. Let's try a few examples. Okay, so I have a little bit more than just an x in my exponent position. So I can think of this more as e to the u, can't I, where u is 4x. So the derivative of y will be equal to e to the 4x, it is itself, multiplied by the derivative of that exponent, and that's going to be e to the 4x then multiplied by the derivative of 4x is 4. I guess I would rather write that as 4 e to the 4x. Kind of the same rule applies here. This is like my u. So I'm going to have y prime equals. It is itself, just get used to saying that to yourself, multiplied by the derivative of that exponent. And that will give us e to the negative 5x, it is itself, and then the derivative of negative 5x will be just negative 5. Because this x has a power of 1, right? And the 1 comes down, multiplies by the negative 5, and then the exponent of x goes to 0, and x to the 0 is 1. This will be negative 5 e to the negative 5x. which we also could write as negative 5 over e to the 5x. Since that's a negative exponent, we could drop it down. And finally, letter J. Now, it kind of looks like product rule when you first analyze this, but think about this e squared for a moment. E squared is like saying I'm taking 2.718, because that's approximately e, and squaring it. That's just going to be some number. So really, for this x, I have a coefficient. This is really e squared times x minus e to the x. If I take the derivative of this, I can use power rule where this power of x is 1. So the 1 comes down and I get e squared. And then x goes to a power of 0, which will give us just the value of 1. Minus the derivative of e to the x now is itself. You could think I've got to take the derivative of x, but the derivative of x would just be 1 and brings me right back to e to the x. Letter K and L, we just got 2 to go. Find the equation of the tangent line to the graph of the given point. Well, in order to find a tangent line, we need to do a first derivative, and that will get us our slope, right? Once will get us the general equation for slope, but I'll have to put it in the slope at a point. Okay, so what we want to do is take the derivative of k. But if you've caught on, natural log and e, they will cancel away each other, and we'll be left with y equals 3x squared on this one. So this becomes kind of old school one. Let's take the derivative of 3x squared, and we're sitting with 6x. Evaluating this at the point of 2 will give us 6 times 2, or 12. And you know, I think this is bothering me. I would like to show that I'm evaluating this derivative at 2, so I'm going to put y prime of 2. Y prime of 2 gives me a slope of 12. Writing the equation, I have my xy location. I'm going to have y minus 12 equals 12 x minus 2. If I need to slide it into slope-intercept form, I can do that just with a little bit of algebra. And I'm going to get y equals 12x minus 12. Final equation here. I am looking at this and I think I see a product rule coming at us. So let's do product rule to get our derivative. F prime of x will equal derivative of the first. Well, the derivative of e is always itself, and then the chain rule. And the derivative of negative x will be negative 1, multiplied by the second function, addition. So this was like f prime times g. Now we're going to go into the g prime times f. Derivative of the second. The derivative of natural log, that was the last section we worked on. That's 1 over x multiplied by the first function, e to the negative x. There's not a lot to simplify on this. We could have f prime of x equals negative natural log x over e to the x, because of this negative exponent, negative x, dropping it down, plus this will shift down too, and I'll have 1 over x e to the x. Let's evaluate our derivative and find out what the slope is when we're at x equals 1. So we're evaluating the derivative, f prime of 1. So I get negative natural log of 1 over e to the first plus 1 over 1 times e to the first. Fairly nice numbers. Natural log of 1. That's basically asking the question, e to what value equals 1? That value would be 0. So I end up with negative 0 up on top divided by e. Well, that's going to be 0, isn't it? plus 1 over e, and so I get 1 over e as my answer because this is going to 0. There's our answer. Oh, that's our slope, isn't it? F prime of 1, that's our slope. Now what we have to do is write it in equation format to get the tangent line equation. So I'm at the point of 1, 0. I'm going to have y minus 0 is equal to 1 over e is my slope, x minus 1. If you want it in slope-intercept form, I'd have 1 over e times x minus 1 or x over e minus 1. Your choice. Okay, we will work on homework tomorrow in class, and it's going to look something like that. Good enough.